The NV Marine exhaust gas cleaning system diverts exhaust gas from the main and auxiliary engines and channels it through the scrubber. SO2 is neutralized by seawater, which is then discharged overboard. Here we see how the exhaust gas passes through the scrubber. Two seawater supply pumps are installed to deliver seawater to the scrubber. These pumps are located in the lower engine room. The location and delivery of these pumps is specific ship to ship. Suction is drawn from a modified sea chest through a strainer. The seawater suction and effluent discharge valves are hydraulically actuated butterfly valves with both local and remote actuation. Each valve has a limit switch that inhibits the scrubber system from running if it is closed. Each seawater pump has a suction and a discharge valve. These are manually operated butterfly valves located adjacent to the pumps. The discharge valves let into a common manifold that then leads up to the scrubber. Each seawater pump is controlled by a variable frequency drive. The system's programmable logic controller manages the function of the pumps, but there is a local control panel on the VFD cabinet. The VFD cabinets are located in the engine room. The exact location is specific ship to ship. If the VFD fails, the seawater pumps can be controlled locally on the cabinet, but only to 0 or 100%, off or on. If a pump fails, a pressure transmitter located at the pump outlet manifold will signal the process controller to shut that pump down and start the standby pump. If a suction or discharge valve is closed when the pump is started, the pressure transmitter at the outlet of the pump will signal a shutdown and the standby pump will come on. If the standby pump has the same problem, the system will not start. There are two large titanium gas quench and conditioning ducts. One receives exhaust gas from the main engine. The other converges exhaust gas flows from the multiple auxiliary engines. The GQCs are located in the scrubber enclosure on top of the scrubber inlet box. Exhaust gas is redirected from the funnel to the scrubber by way of three-way dampers. These are located on the upper levels of the stack enclosure. The dampers are designed such that there is always a flow path for the exhaust gas. In the event that a damper fails, it will default to the scrubber closed, stack open, or scrubber bypass position. There is one large damper to divert the flow of exhaust from the main engine exhaust stack into the exhaust duct for the MEGQC. Each auxiliary engine has its own stack and damper that direct that engine's exhaust flow into the exhaust duct for the AEGQC. Here we see two examples of the cross-sections of the diverter damper valve and disc construction. Here we have a diagram illustrating the flow of sealing air through and around the diverter damper valve disc when it is in the closed position. Note that when one flow path is closed, the other, to the right, is open. Two blowers provide sealing air to the exhaust gas dampers. These are located on the upper levels of either the stack or the scrubber enclosure. Each blower discharge is followed by a check valve. The blowers converge into a single flow path. Only one blower is operated at a time, and the other functions as a standby. The AEGQC duct has 4 spray pipes that supply quenching seawater. 2 manifolds supply the spray pipes. A manual butterfly valve, followed by a pneumatic butterfly valve, controls seawater flow to the lower manifold, while a single manual butterfly valve controls flow to the upper. All supply valves are located in the scrubber enclosure. The exact location of these valves may vary ship to ship. The scrubbing action in the turbo head relies on the exhaust gas flow to produce turbulence. When the main engine is not running, the reduction in gas flow causes a loss in scrubbing efficiency due to less turbulence in the heads. To make up for this, all 4 spray pipes in the AEGQC will spray water for extra sulfur removal inside the GQC duct. When the main engine is online, only the upper manifold of the AEGQC duct will provide spray, which also keeps the lower spray pipes cool. Here we see a diagram that illustrates the layout of the 4 AEGQC spray pipes for further clarification. A single manifold supplies seawater to the two spray pipes in the ME-GQC duct. A manual butterfly valve, followed by a pneumatic butterfly valve, control flow of seawater to the spray pipes. The manifold tees off the lower AE-GQC supply line. The ME-GQC control valves will be found adjacent to those for the AE-GQC. The exact location of these valves will vary ship to ship. The GQC ducts let into the scrubber inlet box where exhaust gas is further conditioned. A manual butterfly valve supplies seawater to the inlet box spray pipes. This valve is located near the GQC manifolds. The inlet box, like the GQC ducts, is made of titanium. This means that it is dissimilar to the rest of the scrubber. The titanium must always be isolated from the stainless steel using Teflon or PTFE to avoid corrosion. There are two turbo heads inside the scrubber tower that do the majority of the removal of sulfur from the exhaust gas. Each scrubber head has spray pipes that provide seawater for absorption and neutralization of the sulfur dioxide. The interaction of seawater and exhaust gas at the turbo heads creates a froth that extracts the sulfur dioxide from the gas and captures it in the liquid water, which is then discharged overboard. A set of demister vanes at the top of the scrubber reduces the amount of water mist released to the atmosphere. These are rinsed once per hour for 2 minutes. A demister booster pump pulls seawater from the scrubber supply and directs it to the spray pipes. Pneumatic butterfly valves control flow of water to the nozzle arrays. The demister spray pipes are located near the top of the scrubber. The demister booster pump is located in the scrubber enclosure. The scrubber can be rinsed for cleaning using fresh water through the demister spray array. A freshwater pump pulls water from the ship's freshwater tank and delivers it to the scrubber. The rinsing schedule is at the operator's discretion. It is recommended to rinse the scrubber with fresh water for 10 minutes every time it will be shut down for 3 days or more. 10 minutes will consume approximately 4.2 cubes of the ship's fresh water. The continuous emission monitoring system is the most important component of the EGC system as a whole. The SEMS allows us to know that the EGC is working by measuring the amount of sulfur dioxide and carbon dioxide in the exhaust gas after scrubbing. The system is class approved. The probe inserted in the top of the scrubber continuously draws an exhaust gas sample from the stack. This illustration provides a cross-sectional view of the sample probe inside the stack for your reference. The gas sample from the probe travels through a heat-traced hose to the analyzer cabinet. All traces of water and residue are removed by the internal cooler and filter. Then the sample is analyzed for gas content. The conditioning cabinet should be kept below 55 degrees Celsius. The SEMS functions best when it is cool and clean. Monitor the unit and ambient temperature and apply cooling as necessary. Clean all system filters regularly. All effluent from the scrubber flows through a single glass-reinforced epoxy or GRE-lined pipe from the scrubber drain tank to the overboard discharge. A manual butterfly valve allows effluent to flow from the drain tank. The GRE drain line travels through the engine room towards the overboard discharge. Prior to being discharged overboard, the effluent is mixed with the ship's cooling seawater at a T-junction like the one illustrated here. This dilution raises the pH to 5 or more. A diffuser on the skin of the ship helps effluent mix with seawater upon discharge. The discharge is located in the lower engine room aft of the sea chest. The exact location of the discharge will vary ship to ship. The water monitoring system samples incoming seawater and scrubber effluent. It alternates every 2 minutes between the two sources using a 3-way pneumatically actuated valve. Measurements of difference in turbidity and PAH between the sources are used to generate a 14-minute rolling average to compare with the IMO regulated limits. An internal pump provides a steady flow of water to the analyzers. Scrubber effluent is monitored for changes in pH, PAH, and turbidity compared to incoming seawater. The PLC control cabinet is located in the engine room. The exact location of this cabinet will vary ship to ship. The control panel in the engine control room is a slave to the panel on the PLC. This means it is only operational if the PLC is functioning. However, if the ECR HMI fails, the PLC HMI will remain functional. In order to operate the system from the ECR, the PLC HMI control right must be switched to the off position. This screen allows for an overview of the scrubber operation. The demister booster pump can be controlled from this screen when in manual mode. This screen allows for an overview of the seawater system. The seawater pumps and the three-way effluent sampling valve can be controlled from this screen when in manual mode. This screen allows for an overview of the freshwater system. The freshwater pump may be controlled from this screen when in manual mode. This screen allows for the operator to acknowledge and view history of alarms in the scrubber system. A digital record of the alarms can also be exported to USB from here. This screen allows the operator to view a log of discrete events in the automation. A digital record of these events can also be exported to USB from here. The following 6 slides show screens that allow the operator to view setting and alarm points for the scrubber system sensors. This screen allows the operator to view the scrubber pump settings and operational set points. This screen allows the operator to view a tabulated history of system parameters. A digital record of these parameters can also be exported to USB from here. This screen allows the operator to view the operating range of each sensor. This screen provides a flowchart of the scrubber system logic for automatic operation. This screen allows the operator to view a linear history of certain readings over a selected time frame. These readings are the SEMS, gas pressure, gas temperature, water quality, effluent pH, water flow, and drain tank level. This screen shows the cumulative running time for each pump in the scrubber system. The system will automatically select to run the seawater pump with the lowest hours. This screen allows the operator to view the vessel's time and location as transmitted by the GPS. This screen allows the operator to set the effluent discharge parameters to meet the vessel general permit standards. To start up the NV Marine scrubber, the operator begins by Step 1. Opening all necessary manual valves. Step 2. On the touchscreen, press Auto. Step 3. Select SECA or Ocean as appropriate. Step 4. Execute VGP if applicable. Step 5. Press the green System Start button below the display. These steps will initiate the following. The power monitoring system will give permission to the PLC to start the seawater pump and supply flow to the AE-GQC, the ME-GQC, the GQC inlet box, the upper turbo head, and the lower turbo head. After 1 minute, the dampers for the running engines will automatically redirect exhaust gas flow into the scrubber. The flow of seawater to the GQC system and the turbo heads is maintained by the VFDs for the pumps and the control valves for the various spray manifolds. If an engine is started or stopped while the scrubber is running, the dampers will actuate automatically to divert the exhaust gas as needed, and the seawater pump will adjust flow accordingly. The priority of seawater flow control for the scrubber program is as follows. First, total flow control to meet the sulfur-carbon ratio. Second, total flow control to meet the scrubber outlet lower pH limit. Third, maintain the temperatures in the GQC ducts above minimum. Fourth, maintain the pressure drop across the upper head. Fifth, maintain total pressure drop across the scrubber tower. The primary scrubber logic is as follows. If the sulfur-carbon ratio is above the set point, then the system will increase seawater flow. If the sulfur-carbon ratio is below the low set point, then the system will decrease seawater flow. If the discharge pH is below the set point, then the system will increase seawater flow. If the GQC temperature is above the set point, then the system will increase seawater flow. If the sulfur-carbon ratio, the pH, and the GQC temperature are all within normal range, then the system will make no change. After shutdown of the main engine and auxiliary engines, or switch to low-sulfur fuel, the scrubber can be shut down by the operator by pressing the red System Stop button. If the scrubber is going to be shut down for 3 days or more, a fresh water rinse should be conducted. The shutdown sequence is as follows. First, all diverter dampers go to bypass positions. Second, the flow of seawater to the scrubber continues for a 10-minute cooldown. Third, after 10 minutes, the flow of seawater to the scrubber is shut down. Fourth, the system prompts a freshwater rinse. This is to be completed at the operator's discretion. If the emergency stop is activated, the following will happen simultaneously. All dampers will return to scrubber bypass positions. The seawater pumps will shut down. The demister booster pump will shut down. The freshwater pump will shut down. All pneumatically actuated valves will return to their default positions. The system will remain this way until it is manually reset.